you, Nathaniel. Also, thank you for the invitation. So if someone has a question, I mean, you can use the chat, but I'm not sure I will be able to see it. So just either interrupt me or ask Nathaniel to interrupt me. Then the question will get through. And please do interrupt me when you have a question. Anytime will do. So I will talk about weighted register automata. And of course, you don't know yet what it is, but I will give a little teaser about what kind of things we are trying to solve. So, by the way, this is joint work with Mikołaj Bojancik and Bartek Klim. We wrote a LIX paper and it's accepted. So you will see a short version of this presentation at LIX. But this is, of course, the good version of the talk. So let me give a little teaser. So we are dealing with register automata. These are like normal automata. And in fact, if you look at the deterministic register automata, all the things which you would expect to be decidable are decidable. So emptiness, universality, equivalence is all decidable. But of course, it's in the name, it has to be some extension of automata. And you will see this when you go to non-deterministic register automata. So here things become undecidable. Not everything. So it's still a pleasant model to work with, but some things are undecidable. And so even without knowing what these things are about, this is an interesting thing, because normally non-deterministic automata and deterministic ones are as expressive. So there's no, you can always determinize a non-deterministic one. Here, that's not the case. So a natural question is, well, where does this boundary between undecidable and decidable lie? And there has been a recent breakthrough by Mortet and Quas in 2018, showing that unambiguous register automata have good decidability properties. I put little stars there because it's a bit subtle, it's a bit nuanced. And here we are going to need a bit more about the register automata. They are parameterized by their data domain. So you can have automata working on different data inputs. And depending on this, it may be decidable, it may be unknown. And there's also two flavors of these automata, guessing or non-guessing. And the results are in this little table. I think they have extended by now. So sometimes it's decidable, sometimes it's still unknown. What we show with our techniques is that all these cases can be proven to be decidable with a single and uniform proof. So this is, of course, what we're kind of aiming for, but actual contribution is the underlying mathematics. And this will be also, this I will try to explain to you. So this is in the end, kind of the exciting part. It's not so much the applications to unambiguous automata, but it's really these weighted register automata and also the type of vector spaces we will see later in this talk. Okay, so this is a little teaser, so you get an idea of the landscape we're in. Okay, so the outline of the talk is as follows. I start with the preliminaries. I have to discuss weighted automata and register automata, because then we can merge them. And then I will go to the decidability of equivalence. And from this, you can also get universality. And this will be the hard part of the talk. And here we need some kind of vector spaces and we need kind of cool stuff. And then I will show you these applications to unambiguous automata. Okay, so let's get into it. I think most of you already know this stuff, but I will still explain this because we kind of need not only the definitions, but also the intuitions for this automata. So here's a weighted finite automaton. It has 3 states. The input alphabet is simply AB, as we always use in automata theory. And the weights come from a field, and in this case, I'll just take the rational numbers. So those are the numbers you see here. There's a 2, there's another 2, here's a -1. And whenever there's an edge without a weight, it has a weight of 1. So here I didn't write it, but there's an implicit 1 there. Of course, when there's no edge, it has weight 0. And so what does this accept? It doesn't accept words, but it accepts words with a weight. So let's do a few examples. So the empty word, so there's one initial state, it's the most left state here. And so when we read the empty word, we start there. We don't take any transitions. And this state does not accept, because there's no outgoing edge. Only these 2 states have an acceptance. And one of which is -1, and the other one is simply 1. But this state does not accept anything. So the weight for this word is 0. Okay. Second example is an A, a single letter A. We start here, and then we could take this loop here. And then by then we have accumulated this weight here too, but in this state we won't be accepting. So this run has weight 0. But there's a second run. We can start here, then take this transition, we end here, and this will accept. And this run has weight 1. So the total weight for A is 1. We can continue with putting more A's into the word, and let's see what happens. Again, when we end up here, it won't be accepting. So we'll look at runs accepting in the second state. So one such run is, as before, we start here, we go there, and then take a second loop like this. Here, we have to multiply all the ways along the path. So what we do is we start here with weight 1. We take this first transition with weight 1. Then we take the second transition and it has weight 2. So this run has weight 2. But there's a second run we have to consider, namely the run starting here, taking this loop, and then going to that state. Again, first loop has weight 2, and then the transition has weight 1. So the total weight for this run is 2. And the total weight for this word, AA, is 4. And similarly for 3 A's, there's now 3 runs we have to consider. We can take 2 loops here and then accept. We can take 1 loop here, transition, and then take another loop, or we immediately go to the second state and then do 2 loops. Each of the runs has weight 4, and there's 3 of them. So we get 3 runs of weight 4, and we get weight 12. Okay, so I hope you can see how this kind of goes, this game. You look at the different runs through the automaton, you add them up, and then this will be the weight. And so for a general word AN, the letter B will come in a second. We have n different runs, each of weight 2 to the n minus 1, if I'm not mistaken. And for the B, we, well, that's kind of a single transition down. So we just end up there, and then we get a -1 weight. So the weights can be negative as well. That's not a problem. And so if you have several runs, they might cancel out. It doesn't happen here, but this might happen. So the word BW, because of this loop here, which has a weight 1, simply has weight -1 because this has an implicit weight of 1. If we do AN followed by a B and followed by some words, we get a -2 to the n, because we will have to take these transitions first, then we do the B, and then we have this negation in the end. Okay, so even if you have not seen these automata before, I hope the intuition is clear. So here will be the definition. So we fix a field. So this can be a field like the rational numbers, but it could also be a finite field if you like. There's a finite set of states, Q. There are initial and final weights for each of the states. And there's a weighted transition function. So for each letter in the alphabet, there will be basically a matrix given as such. And then the semantics is, as I explained, given a word, you look at all the runs through the automaton, and you multiply the weights of your starting state. Then you multiply by all the weights of each transition in between, and you multiply by the final weight. So if each of these things will be 0, then of course this run doesn't count. It just doesn't matter for the sum. So we will only be looking at runs starting at the non-zero initial state and going to a non-zero final state and taking non-zero transitions in between. There's a second way to look at these weighted automata, and this will be important for our talk. And that's when you look at the configuration space. So instead of looking at runs, what we will do is we look at an ambient space Rn. So in this case, V will be R to the 3, because we have 3 states. And we look at linear combinations of states. So we start, if we call them X, Y, and Z, we start in an initial vector 1, 0, 0. And then when you do an A transition, there's 2 transitions, but then we can go to a single new vector, namely you take this loop here, which means that you will end up in a state, well, 2 times the x kind of thing. And there's one transition here, which means that your x value is now moved to the y value of a component. So you can kind of unroll this automaton inside this vector space, and you get well, you get still kind of an automaton, but now it will be an infinite state space. So if you do another A, it will be 4. This will also be 4 and then 0, I think. And you can kind of unroll this whole automaton like this. And this is the configuration space. And what you will notice, yes,
there's a quick question by Uli. He's asking if it matters that you're only considering fields. So I guess it will matter later in the talk.
It will matter for the decidability. For these definitions, it doesn't matter. But if you want to know where it matters in the decidability, maybe you can ask later again, because I have a bonus slide at the end.
Okay, thank you.
Okay. Okay, so we're unrolling this automaton, but what you will notice is that you will get a vector space of finite dimension. There's an initial vector. These, the final weights will be a linear map, in fact, and the transition function will also assemble into linear maps. So instead of looking at this as a matrix, you now consider this as a linear map between on V to V. So I think this is particularly elegant because it's somehow an easier definition of an automaton. Of course, you find the basic object is maybe a bit more complicated. It's a vector space instead of a finite set. But then all these other structure maps, like the final weights and the transition functions, those are really just easy linear maps. And then you can define the semantics in terms of matrix multiplication or just composition of these functions. So this will be very useful to understand this. And if you define an automaton like this, it's exactly the same as a weighted finite automaton as I defined before. They accept the same class of functions, so weighted languages. Okay, that's enough about the weighted automata. Let's go to register automata. So again, we have a finite set of states, but here one of the states in this case has a register. This is kind of like a little cell of memory where it can store a value which it read before. In general, you can have multiple registers and also among multiple states. In this case, so someone is asking something, but I cannot read the full question. So these register automata, they will act on a infinite alphabet. So in this case, I will take the natural numbers. Without further structure, you can just compare them for equality or inequality. And how this works is as follows. These transitions are now annotated with updates. So you can store values in this little memory cell, and you can compare values with these cells. So let's again do a few examples. So we take an infinite alphabet, and we start again with some simple words. We start here in the first state. It's not accepting. And so with just epsilon, we will not be accepting. With just an A, well, there's 2 transitions we could take. So we start here. We could take this transition, not be accepting, and we could start here and then take this transition. We will store the A, but again, this state is not accepting. So neither of these words will be accepting. Let's do AB. This is a bit more interesting. So let's ignore the case where we take a look. We can do an A. By A, I mean just any natural number, by the way. We go to the state. We store it in the state. And then when we read the B, we can take this transition provided that B is equal to the value inside the register. So this will be accepting if A is equal to B. And it will be rejected otherwise. Okay, let's do ABC. So let's see, what can we do? We can, again, we can do AB as before. So we can do A and then B. If A and B are equal, then we will be accepting. What we also could do is we store the A, we skip the B, and then read the C, provided that C is equal to A. This will be another accepting run. There's a third option, which will be to skip A, then read B, store it in the register, and then compare to C, the last letter. So this will be accepting if A is B, or B is C, or A is C. I will be rejecting otherwise. Well, A is a special case of the AB we said before, so this will always be accepting. ABCB will also be accepting because there's a B which is repeated. So you can take, you can skip the A, store the B, you skip the C, and then read another B, which will be accepting. And AABCD will also be accepting just for the first two A's. Okay, so here's a somewhat definition of such a structure. So we fix a data domain A, and we typically use the alphabet of this shape. So in this example, I didn't use X, so X would be just a singleton set. But in most applications, you can think of, for example, X being a finite set of control messages, like in a protocol, you have SYN and acknowledgement and close. And then the A part will be maybe sequence numbers or identifiers, which you have to compare in the protocol. These typically come from an infinite domain. So that will be the input alphabet. The automaton consists of a finite set of locations, a set of registers per state. So in this case, I have only one state with a single register. There's initial and accepting locations, and there's a bit of a complicated transition structure because we need a syntax to have these updates, and we need a syntax for these guards, those Boolean guards. And I will not specify these for the talk. I hope you have some intuition in what you can put there. It's a bit technical. And acceptance is, as you would expect, the word is accepted if there is a run starting in the initial set, ending in the final set. And then for each transition, you have to do some bookkeeping with the which values are contained in the registers and whether this transition is allowed or not. Okay, so you will have to remember which values you have read before and store them in the configuration. So this definition is a bit cumbersome. So I will actually define it in a different way. And again, we do this by looking at the configuration space. So for this example, if we label the states Q0, Q1, and Q2, configuration space will be simply Q0 and Q2. They don't have registers. And Q1 together with every value for the data. So in this example, I took the natural numbers. So let's use that. Okay, so we're just going to unroll this automaton as before, but now we unroll in the sense of we look at all the evaluations for the registers. We keep the non-determinism, however. So if you want to picture this, you can start in Q0, and then you read, for example, the natural number 0. And there's two options. You either stay in the location or you go to the new state Q1 with the value of 0. Similarly, for the value 1, you can take the self loop or you go to Q1 with a value of 1. And so you will get infinitely many transitions like this. And we can further enroll it. We can have another 0 here. We can also accept when we read the second 0. And so on. Okay, you can do this. It will be an infinite automaton, infinite state automaton. But you will maybe notice that there's a lot of structure in this automaton. And the structure we need is that of a group action acting on this. So we can look at bijections on the, in this case, the natural numbers, that was my alphabet. So bijection pi. Then this bijection also acts on the state space Q, fancy Q. Because if we, for example, swap 0 and 1 as natural numbers, we can swap these. Sorry, something happened on my screen. Then by such a permutation, we can also swap these two states in the infinite state automaton. Okay, so it's not just any infinite state automaton, it has a bit more structure. And in fact, what you can do is, first of all, you can group these different states into equivalence classes. These are called orbits in group theoretic language. And then what you can do is you can say, well, we say this automaton, which we define it as an orbit finite automaton, meaning that the state space is orbit finite, so finitely many orbits. The set of initial and accepting states have to be invariant under this permutation. So in this case, that is the case. So this would be the set I, and this would be the set F. And if you look at what the action does here, it just sends Q2, 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 and always. Also Q0 would be a fixed point. So those are equivariant subsets. And this transition relation now, which is of the type of an automaton, really the simple type, is equivariant as well. So also this behaves well with the permutations. So I've now shown you how to go from a register automaton to an orbit finite automaton, but there's a converse to this. If you have an orbit finite automaton, you can always find a register automaton which exactly accepts the same language. This is provided some conditions which I will not go into, but this is a more semantic definition of a register automaton. And that's important later in this talk. So the way I see register automaton are like this. They are orbit finite automata. So there's some kind of group structure which acts on the state space, and with this action, there's finitely many orbits and so on. Yeah, okay. So for weighted automata, we use linear algebra. And for register automata, we use group actions. So when we want to combine the two, we will do linear algebra with group actions. Okay. So this will be kind of the setup we're going to look for. So here's a weighted register automaton. Again, when I don't write a weight, it has a weight of 1. So all the arrows you see here are actually annotated with weight 1, and we will be adding several runs to get the weight for the word. There's also the register structure, so there's this memory cell here, and we can store values in there. Again, my alphabet will be that of the natural numbers, not just any countably infinite set with no further interesting structure. And let's do a few examples. So again, the empty word, you will start in this location here, but this is not an accepting location, so it has weight 0. If we read a single A, you start here. You could take this transition, of course, but it will lead you to a non-accepting state. So you go to this state. You store the A in the register, and this state is accepting. So this will have weight 1. Now you read AA. You could try, as before, to go to the first state, then store the A. But now look what happens. You can only take this transition when the value you read is different from the register. We have just stored A in the register, so this transition we cannot take. So the run which you start like this has weight 0. There's no enable transition here. So in order to do AA, what you can do is you take the first loop and then you go there, and then you will have a weight of 1. So this has a weight of 1, but with a different run than before. What about AAB? You can do the same run as before. You do A. So let's say A is unequal to B for simplicity. At this point, you have stored A in this register. Now you can take this B transition. So there's at least one run where you accept this word. But what you could also do is you can skip both A's, then take a B transition, store the B, and accept. So this has weight 2. Similarly, AB has weight 2, where the first A and B, they have to be skipped. Because if you store them, then the second A will kind of not work anymore, or the second B. ABC has a weight 3. Because once you store the A, you can read B and C. Again, I'm assuming that this means that A is unequal to B and B is unequal to C and A is unequal to C. In general, this automaton, it accepts the following. For every word, it counts the number of distinct data values in the word. I think this is quite nice already. So this is an example of a weighted register automaton. I will not give a definition. I hope you have kind of the creativity to think of a definition yourself, given that we spent some time on weighted automata and register automata. What I will want to do is now look at equivalence. So given two of these automata, we want to decide the following. For every word, are the weights associated to those words equal? That's the question we want to decide. And this is not an easy thing to decide because, first of all, there are infinitely many words. Second of all, the input alphabet is itself infinite, right? And then third of all, we are comparing quantities. So it's not at all trivial that this would even be decidable, but it will be. And what we are going to do is we're going to actually use the same algorithm we would use for weighted finite automata, where the alphabet is finite.
So
and this
there's
is
a question here.
Yeah.
Could you do less than equal to as well? Because I'm just looking.
Yeah, so this is a good question. I will say it here in the corner. We can do the simple structure as I showed. We can also do a dense linear order. But these are the two only things we know we can do. And there's actually one case where we know our techniques won't work. This is not to say it's indecidable, that I don't know. Again, if you want to know more, there's a bonus slide at the end. So please then repeat the question. No.
Can you do pure inequality?
So this we can do, yeah.
Oh, no, this is less than equal to, but I just want to say not equal to.
Oh yeah, that you can do. Yeah.
So because by complement.
Yeah. Okay. So when I write a structure like this, you can also do all Boolean combinations.
Great.
Yeah. Okay. So how do you do this equivalence for weighted finite automata? First step is to reduce it to checking whether automata are zero. Because if you have two automata, you can subtract one from the other with a kind of product construction. Well, it's even easier than a product construction. And then you check whether the language is equivalent to zero. So how do you decide whether a given weighted finite automaton accepts zero for all the words? And here is where we're going to use linear algebra. So recall that the ambient space is R to the n. So in this case, we have R3. And we can do some kind of reachability analysis, but then in terms of this vector space. So here, again, if you say x, if you give them names like this, we started with the vector 1, 0, 0. With an A transition, we went to 2, 1, 0. And with another A transition, we went to 4, 4, 0. And notice what happens here. If we start here and we look at the vector space spanned by this vector, it has dimension 1. If we now look at the first two states in this kind of unfolding, it will have dimension 2. Right? Because the first component is kind of independent, and then we could subtract this from this, and we get the second component also independent. So we have dimension 2. If we now look at the third vector here, nothing is added. This vector was already inside the vector scope, vector space spanned by the previous two states. Okay, so this is hopeful. I mean, this kind of means that we can at some point stop this search. So let's make this more precise. So we have this, we are inside this R to the n, that's our ambient space, and we're going to define these subspaces. These are the linear spans of states reached by words of at most length I. Okay, so we're going to gradually increase the length of the words. This creates bigger and bigger subspaces like this. And the question is, will this ever kind of stabilize? Because if it does, then there's only finitely many things to check. So how long can such a chain of inclusions be? And if you have a proper inclusion of two subspaces, the dimension will go up at least 1. And since this has dimension n, such a chain of subspaces can be at most length n. Because each time there's a proper inclusion, you have to jump by dimension 1, and then you can only do this n times, because then you have dimension n. So such a chain of subspaces has at most length n. And then together with this property, if on every vi the final weight gives 0, then the automaton is equivalent to the 0 language. And what I mean here by I is really every I from 0 to infinity. So let's put it like this. But since this chain is finite, you only have to check this for finitely many I. And this is how you get a decidability procedure. You know the bounds on this chain, and then you know there's only finitely many things to check, and you check those things, and then you know. This is a method from the 60s by Schuch and Berger. I think it's very elegant. I mean, you're really using linear algebra here in a nice way. Okay, so this is what we want to generalize to our weighted register automata. And let's see how this goes. So the key property was that the length of a vector space, by which I mean the maximal chain of subspaces, is the dimension of the vector space, and which is just n. This does not work for the register automata. And let's go back to this example. So what are the vectors here? So we start in some kind of initial vector. Say this is state, let's call it Q0. No, let's call this big X and big Y. This register is a small x. It will not really matter here. So you start with some kind of initial vector like this, 1 and then 0. I will kind of not put a closing bracket yet. Then you read a symbol, say you read the natural number A. Then you get into a new state, new vector. So you are still in the X because there's a self loop. But you also make this transition to Y. But you make a transition to Y with a specific value for this register, which is now A. So A is, let's say, in the input alphabet. So you will have, this is the X component. There will be a Y component with the value of A in it. And you can see if you then read another value, say B, there's 3 components which you need. You need the component for A, for A, you need a component for B as well. And so what you actually end up with an infinite dimensional vector space, where for each possible data value, you have a Y component, which remembers whether you are in this state with specific Y or not. Okay, so the configuration space of these weighted register automata are infinite dimensional. So this kind of, we have to do a bit of work here, right? Because it doesn't trivially work, this algorithm. But remember that we don't care about the dimension, we care about the length. So maybe that's still finite. Who knows? Yeah, so this space is infinite dimensional, but we care about the length. So what we have shown is that indeed the length will be finite, but we have to define length in a certain way. We want all these subspaces to be equivariant. So recall that we have this group action on these data values. And so this group action also acts on the vector space. And we want these subspaces to be invariant under the permutations. And if we then look at chains of subspaces with this property, and then define the length as the maximal chain, then we can show that for these data values, we have for each set of k tuples, if you then take that as a basis, it has finite length. This is the key theorem here. And this is something we had to prove. We couldn't find this anywhere in the literature. But this is the key theorem. And let's kind of look at what this means. So I will look at the linear span of just the atoms. So A is, I will take the atoms where they're just the natural numbers with equality, so all the permutations. And we look at we take this set and we take it as a basis for our vector space. So how does this look like? You have all these, say, points. So you have maybe element 0, element 1, element 2, element 3. I don't really care about these labels because I will be able to permute them anyways. So I'll remove them again. There's just a set of points and you can permute them. And in this vector space, you can assign weights to these points. So maybe this has weight -1, this is weight 17, this maybe has weight 5. And such a linear combination is a vector in this space here. So V is in this space, and this could be one of the V's. This is like a little, and there has to be a finite linear combination. So only finitely many of these atoms will have a weight, a non-zero weight. Right, so this is a vector. You can see that you can also have vectors which have really a lot of weights to them, and can be very big. What kind of subspaces can we define here? Equivariant subspaces. Well, we can try to, for example, pick one of the vectors. Say we take maybe two points, and we say, well, both of them have weight 1. So let's say this is maybe to take A and B in A distinct. And I take this vector, A plus B, and I take everything spanned by this. By spanned, I mean linear combinations, but also closed under permutations, which we require them to be equivariant in subspace. We can consider this. This will be a subspace, simply spanned by one of the vectors. In this case, we can actually show that this is the whole space, surprisingly. And this is how that goes. So we have A plus B as a vector. Because this is closed under permutations, you also have A plus C in the same vector space. And now we can subtract the vector B plus C, also again by permuting these A's and B's and C's. And if you then add 3 vectors together, you will get 2 times A. So what this shows is that 2 times A is in this vector space. If you're now working with characteristic 0 or 3 or more, then you can divide by 2, and you see that the element A is in this vector space, and well, A is also how this whole space is defined, basically. So we tried now to make a subspace, but we kind of failed. Okay. So let's try something else. Let's try a vector A minus B. Will this be a subspace? Well, how would you know, in fact? This is not easy to see. So here, there's the trick. In this case, you can write this as a kernel of the following map. So a general vector here can be written as a formal sum of certain weights times these basis elements. And we can map this to just the sum of the weights. So we forget the elements, so we could just map to the field, just adding all those weights. And then this is the kernel of this map. And since this map is non-trivial, this kernel is also non-trivial, but it's not the whole space. This map is surjective. So this is an actual non-trivial subspace. So if you want a more concrete definition, you could say this is the set of all vectors V such that the sum of the weights in V add up to 0. So it's exactly all these kind of balanced vectors where if you kind of just look at the whole landscape, it just flattens out in a sense. Okay, and this one can show is a subspace, and there's no subspace in between, and there's also no smaller subspaces. This is a bit surprising, but this is the only subspace. And so this vector space here has length 2. Just to hopefully to give a bit of a flavor of how this theorem works. I mean, it's not so easy to see this in general, but that's the kind of computations you have to make. Okay. Now, from some kind of abstract algebra, we get this following lemma. If you have a space V and a subspace W, then the length of V will be that of W plus the length of the quotient. This is true in a very general setting. You can find this in many textbooks on algebra. And from this, you get a even nicer fact is that if you have a direct sum of 2 spaces, the lengths just add up. It's kind of a reformulation in a sense. And so this is now nice because now we get that for every configuration space, we will have finite length. Because I showed you the theorem saying that the things like this will have finite length. But for a automaton, we have several states with a different number of registers each. And so we will take the additional union of those, and the vector space spanned by this is a direct sum of all those spaces. And this will have finite length. Good. And now we can just repeat the algorithm. We do the same algorithm. We look at all these subspaces, Vi, of all states reached by words of a length at most I. We consider this chain. And now we know this chain will stabilize. The length, by the way, I didn't notice it, but we have a bound which is exponential in the number of registers. So unlike before, where it's simply the length is the dimension is n, we now have a exponential bound on this chain. And we simply check the same conditions as before, and if those hold, then the automaton is the zero automaton. So we can actually use the same algorithm. Of course, there's a few details hidden, but the most crucial thing is that this chain of subspaces will stabilize. And this is a purely mathematical theorem we had to prove, but the algorithm is the same. Okay, enough with the mathematics. Let's see how we can apply this kind of thing. So I told you about the deterministic register automata and unambiguous register automata and non-deterministic register automata. And the nice thing is that these, there's also the variance where we are not allowed to guess atoms. So the minus is just the non-guessing variance, and without minus are the guessing variance. So there's also alternating register automata. They sit even above this hierarchy, and data monoids, which sit on the bottom level, kind of. Each of these inclusions is strict. So unlike with finite alphabets, everything is a regular language. Here, all these classes define different classes of languages. Okay. The crucial thing is that this unambiguous register automata, they embed into the weighted register automata, and this is the reason. So you can always consider a non-deterministic register automaton as a weighted register automaton by simply counting the number of accepting paths. This, of course, changes the semantics, right? If you have two automata, they might compute the same language, but they might do it in different ways such that these weights will be different. But for unambiguous register automaton, there's at most one accepting run. And so the semantics doesn't change. If two unambiguous automata are equivalent, then the weighted ones will be equivalent. And this is an if and only if. So you can embed them. So now we've shown that equivalence is decidable below this line. We in fact also know that it's undecidable above this line. So this is equivalence. We also considered weighted data monoids. They don't really play a role, but these double lines mean that these classes are equivalent. So unlike on the left, where data monoids are very weak, here the weighted monoids are equivalent to automata. And also guessing and non-guessing are equivalent, which is, at least to us, is very surprising. Also, the fact that monoids are equivalent is also surprising to us. There is a class in between. You can extend these unambiguous register automata. You can close them under the Boolean operations, simply because intersection is a multiplication in the field. And then you can do negation by subtracting from one. And then by De Morgan, you get union as well. So you can consider a slightly bigger class of languages and still be able to decide equivalence. This also shows that containment of these languages are decidable. So if you have two languages in this class, you can decide whether one is included in the other. Because you can use union to then rewrite containment as equality. And there's also probabilistic register of automata if you are interested. It sits in the same hierarchy, and also equivalence will be decidable there. So this is kind of a whole landscape which now opens up because we consider these weighted register automata. I think, I think this is quite nice. And they form a very robust class of languages because we have now these equivalences between monoids and guessing and non-guessing. So that's it. Thank you for your attendance, and thank you for the questions so far. I would be happy to answer more questions.
Right. So thanks a lot, Joshua. Let me thank you first of all. Then I'll stop the recording and then we'll start the Q&A session.